तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Pre-stressed concrete structures. This is the fourth lecture of Module 4 on design of members. In this lecture, we shall study the choice of different sections. Then we shall move on to the determination of limiting zone. And finally, we shall talk a little bit on post-tensioning in stages. First, the choice of sections. The type of section is selected based on the use of the structure, architectural requirements, casting and fabrication options, available technology and skilled workforce. Here, a few comments are given for the available types of section. The pre-stressed applications at present are quite varied in nature, and depending on the type of sections, we select the use, and the type of sections can be innovative to meet the requirements. It satisfies the architectural requirement, it satisfies the aesthetic considerations, it satisfies the structural strength. Hence, the choice of sections is quite a wide-ranging topic, but in this lecture, we shall cover the different sections in a summarized form, just stating the basic points of each type of section. The sections here are broadly classified under rectangular section, T section, I section, and inverted T section. Some variations of each type are shown under the corresponding broad groups. The sections in each group have similar analysis procedure. Of course, the sections shown are not exclusive. That means the different types of sections that are available, we have tried to group them under some broad classifications. In each group, the analysis procedure is similar for the primary flexural reinforcement. There can be variations in the analysis depending on the local bending stresses or the transverse bending analysis. The broad groups that we have selected are, first, in the rectangular type of section, where there is no outstanding flange. The second is the T section, where the outstanding flange is at the top. Next, the I section, where the flanges are both at the top and the bottom. And finally, the inverted T section, where the flanges are at the bottom. Regarding variations, again we are showing some typical types of sections with some schematic sketches. A rectangular section can be trapezoidal in nature, where the width of the web varies along the depth. A T section can have a bulbed flange at the bottom. The flange need not be always outstanding. There can be a flange between two webs. For the type A section under this category, there is more room for tendons in the lower flange. The purpose of enlarging the bottom of the web is to place the tendons properly. For B, there is better stability during erection. We can place these members properly, and then we can place a cast in place concrete over this precast members. For the third group, we can have a box type of section, which are more common in bridges, and there can be different types of box cross sections where the webs need not be parallel, and there can be holes in the rectangular section. If the size of the holes is larger than a certain value, then we have to treat this section as a flange section. If the holes are smaller than a certain value, then they can be treated as a rectangular section with equivalent properties. The box sections are torsionally stiff and strong. Hence, as I said, that they are used in bridges, especially for curved decks where the torsional requirement is quite high. The inverted T sections can have variations like U section, and there can be cast in place topping slab over this type of inverted T sections. Now let us study some of the aspects of these different types of sections. The fabrication is easy for a rectangular section, it is easy for even a T section, but it can be quite expensive for a I section, because if we want to cast different sizes of section in a project, then the variation of formwork is also quite expensive. The fabrication for the inverted T section can be difficult in certain locations. Regarding the space of reinforcement, the rectangular section has adequate space. A T section will have less than adequate space unless we enlarge the bottom of the web as a bulb. There is good space for the tendons in the I sections as well as in the inverted T sections. Let us now study the basic properties for this type of sections when they are used as non-composite sections. Regarding flexural efficiency, the rectangular section is poor. The lever arm, which is represented by Z, is about 40% of the total depth, which is represented by H. Compared to a rectangular section, a T section is flexurally more efficient, and the lever arm is about 50% of the total depth. The I section is flexurally very good, and the lever arm is 70% of the total depth. The inverted T section is very inefficient for flexural capacity if it is bending in positive direction, but we can increase its flexural capacity if we are having a topping slab, which we shall mention under the category of composite sections. The ultimate moment capacity for an inverted T section is small as compared to the other types of sections. If we look into the applications of this type of sections as non-composite sections, then the rectangular sections are used for light load and short span, and for this applications the self-weight moment, which is represented as MSW, is quite large compared to the total moment the section has to carry, which is represented as MT. The T section is good for long span roofs when the live load is much smaller compared to the dead load. For T sections also, the ratio of MSW by MT is large. For I section, they are good for long span and heavy loads. Here the MSW by MT ratio is small compared to the rectangular and the T sections. For the inverted T sections, the applications are rather limited. When we use them, the MSW by MT ratio is large. Now let us see the properties of the sections when they are used as composite sections. That means there will be a topping slab above these sections. Regarding efficiency, the rectangular section is very good when the section is shored during the casting of the topping slab. For the T section, the increase in load capacity is only slight if you are having a topping slab of small depth. For I section, the increase in flexural capacity can be very good. For an inverted T section, when we have this topping slab, then its flexural capacity increases substantially. Thus, we see the inverted T section is flexurally efficient only if we have a topping slab in a composite construction. Regarding application, the rectangular sections are good for building construction, where the construction can be done quickly. For T sections, the topping serves to tie all sections together. That means we are placing the T section side by side, and over that, when we are placing a topping slab with some continuity reinforcement, then the topping slab helps to force all the T members to deform together. And for this type of section, we do not need any formwork for the composite pour of the concrete. The I sections, as a composite section, they are used for long span buildings and bridges. We have seen the application of box girders in bridges. The inverted T sections can be used in bridges with cast in place flange at the top. The different types of sections that we have seen can be compared by a quantity called flexural efficiency, which is represented by the symbol eta. The flexural efficiency is defined in terms of the radius of gyration as follows. It is defined as eta is equal to r square divided by Ct Cb, where Ct is the distance of the top from the CGC and Cb is the distance of the bottom from the CGC. To this expression, we are multiplying a factor Ct plus Cb divided by h. This factor is equal to 1 because Ct plus Cb is equal to h, and hence h by h is equal to 1. Then we are breaking the numerator of this factor and writing eta is equal to r square divided by Cb plus r square divided by Ct divided by h, which leads to this final expression eta is equal to Kt plus Kb divided by h. Thus, we have defined a quantity to compare different types of sections regarding their flexural capacity. Just remember that here we are talking of the bending in the primary longitudinal direction. We are not talking of any transverse flexure in this quantity. Thus, eta is equal to the kern zone depth, which is represented as Kt plus Kb divided by the total height. That means for a section of a certain height, if we are able to increase the kern zone, then the flexural efficiency goes up. To summarize, for a given value of the depth h, if the kern zone, which is Kt plus Kb, is large, then the section is flexurally efficient. For a rectangular section, eta is equal to 0.33. For an I section, eta can vary around 0.5. Thus, we see that the flexural efficiency of an I section is greater than that of a rectangular section. Next, we are moving on to another important aspect, which is the determination of limiting zone. This helps us to place the CGS as well as the distribution of the tendons along the span of the beam. In our flexural design, we had studied what is the required eccentricity at the critical section, but now we shall study how to place the tendons throughout the span of the beam. For full pre-stressed members, which are represented as type 1, tension is not allowed under service conditions. If tension is also not allowed at transfer, the compression in the concrete, which is represented as C, always lies within the current zone. The limiting zone is defined as the zone for placing the CGS of the tendons such that C always lies within the current zone. Also, the maximum compressive stresses at transfer and service should be within the allowable values. Thus, the limiting zone is related with the placement of the CGS in such a way that for a type 1 member, the compression in the concrete lies always within the current zone throughout the span of the beam. We also need to make sure that the flexural stresses at transfer and at service are within the allowable value. For type 2 and type 3 members, tensile stresses are allowed, and hence the compression in concrete can lie outside the current zone, but it has to be within a certain limit such that the tensile stresses at the bottom or at the top are within the allowable values. The limiting zone is defined as the zone for placing the CGS such that the tensile stresses in the extreme edges are within the allowable values. Also, the maximum compressive stresses at transfer and service should be within the allowable values. Thus, the definition of the limiting zone is more general for type 2 and type 3 members as compared to type 1 members, because for type 2 and type 3 members we are allowing tension in the concrete, and hence the compression can lie outside the current zone. Remember that when we are talking of the limiting zone, we are just talking of the CGS. The individual tendons may lie outside the limiting zone, provided the CGS is within the limiting zone. The limiting zone is determined from the maximum or minimum eccentricities of the CGS along the beam corresponding to the extreme positions of C. The maximum eccentricity, which will be represented as E max at any section, corresponds to the lowest possible location of C at transfer that generates allowable tensile stress at the top of the section. Also, the maximum compressive stress at the bottom should be within the allowable value. As it is evident from the word itself, the limiting zone is determined by placing the CGS as low as possible such that it corresponds to the extreme position of C. The lowest possible eccentricity, that means the distance of the CGS from the CGC at a particular section, will be denoted as E max, and it is determined in such a way that the compression does not cause a tension at the top beyond the allowable value, or a compressive stress at the bottom beyond the allowable value. Thus, the maximum eccentricity is calculated by lowering the CGS as much as possible by satisfying the stresses at transfer. The minimum eccentricity of the CGS, which is represented by E min, corresponds to the highest possible location of C at service that generates allowable tensile stress at the bottom of the section. Also, the compressive stress at the top should be within the allowable value. Thus, to determine the minimum eccentricity of the CGS, we are allowing the compressive force to rise as much as possible at a particular section, such that the compressive stress that is generated at the top and the tensile stress, if it generates at the bottom, should be within the allowable values. The purpose of allowing the compression to rise above the CGS by as much distance as possible is to have an efficient section. With that, we are able to reduce the amount of pre-stressing force. The following material gives the expressions of E max and E min for type 1 and type 2 sections. As we all know that the difference between type 2 and type 3 sections is just only in the value of the allowable tensile stress. Thus, if we have the expressions for type 2 section, we can use that for type 3 sections, provided we change the value of the tensile stress. The zone between the loci of E max and E min is the limiting zone of the section for placing the CGS. That means we calculate E min and E max at different sections throughout the length of the beam, and once we have determined these values, we join them by a line, one line for the E min values, another line for the E max values, and the space in between these two lines is termed as the limiting zone for placing the CGS of the tendons. The values of E max and E min can be determined by equating the stresses at the edges of concrete with the allowable values. Else, explicit expressions of E max and E min can be used. Here, the expressions of E max and E min based on allowable tensile stress are given. That means there are two ways to determine the values of E max and E min at a particular section. One way is to write the expressions of the stresses at the top and the bottom, equate those stresses to the allowable values. From there, we can find out the E max or E min values. The another approach is try to find out some explicit expressions of E max and E min so that we can directly calculate those values without calculating the stresses. But both these approaches will give the same result finally. Here, we shall show the values of E max and E min based on the allowable tensile stress. For type 1 section, at transfer, we are pushing down the CGS as low as possible to have the lowest possible location of C, which is at the bottom current point. Now, in this figure, we can see that the C is located at a distance kb from CGC, and the tensile stress in the concrete is triangular, which is 0 at the top and FB at the bottom. The lever arm at this stage is governed by the self-weight moment. The lever arm is the distance between the T and the C, which is equal to E max minus kb, equal to MSW by the value of C, which is equal to P0 at transfer. From this, we find an explicit expression of E max. E max is equal to MSW divided by P0 plus kb. This expression is based on satisfying the allowable tensile stress at the top, which is 0 for a type 1 member. We should also check E max to satisfy that the stress at the bottom, which is FB, should be less than the compressive stress at transfer, which is represented as FCC allowable. Next, for type 1 section, we are determining E min. Here at service, we can have a highest possible location of the CGS, I would say a minimum eccentricity from the CGC, such that C is at the top of the current zone, which is at a distance kT from CGC. At service, the stress in the concrete will be a triangular with 0 stress at the bottom and a certain value Ft at the top. If we equate the total lever arm, which is the eccentricity of the CGS plus the eccentricity of the CGC, that is equal to E min plus KT, which is equal to the total moment mt divided by the value of C at service, which is equal to PE. Thus, E min is equal to mt divided by PE minus KT. Here also we find an explicit expression of the minimum eccentricity of the CGS based on 0 tensile stress at bottom during service. We of course need to make sure that the compressive stress at the top, Ft, should be less than the allowable compressive stress at service. If for a particular section E min is negative, it implies that the CGS can be placed above CGC. This happens near the supports. For type 2 section, at transfer, we can push the CGS even below such that C can lie outside the current zone, so that the tensile stress generated at the top is equal to the allowable value. The stress block in the concrete at transfer for a type 2 section has some tension at the top. The distance of C from the bottommost current point is represented as E1, and the distance between the C and T is represented as E2. We can write that the distance between the CGS and the bottommost current point, which is equal to E max minus Kb, is equal to MSW, which is the self-weight moment, plus FCT allowable, which is the allowable tensile stress at the top, times the area of the section A times the current depth Kb, whole divided by P0, the effective pre-stress at transfer. This expression we had seen in our last lecture, and we can appreciate that this is a more general form of expression where we have one term which involves the allowable tensile stress. From this we find an explicit expression of E max equal to the self-weight moment MSW plus FCT allowable times A times Kb whole divided by P0 plus Kb. This expression again is a general form of the expression that we had seen for type 1 member, and this expression has an extra term involving the allowable tensile stress at the top. We also need to make sure that the compressive stress at the bottom is less than the allowable compressive stress at transfer. For service in type 2 sections, we can have C going outside the current region by a distance equal to E3, so that we have a tensile stress at the bottom which is equal to FCT allowable for service. The minimum eccentricity plus the distance of the current point from CGC equal to the total moment mt minus FCT allowable times A times KT whole divided by the effective pre-stress PE at service, or E minimum is equal to mt minus fct allowable times A times kt whole divided by PE minus kt. What we are saying is a general expression of E mean for a type 2 member, which is similar to a type 1 member, just with it has an extra additional term involving the allowable tensile stress in the concrete. And if we substitute FCT allowable equal to 0, then we get back the expression which is for the type 1 member. Also, we need to check the stress at the top to be within the allowable compressive stress under service conditions. The zone between the loci of E max and E min is the limiting zone of the section for placing the CGS for a given loading condition. The values of E max and E min for several sections can be determined at regular intervals along the length of the beam. Thus, we can select an interval of 1/10 of the span for each section depending on the moment due to self-wet and the moment due to service loads. We can find out the E max and E min value for each section, and once we join these points, we get the boundaries of the limiting zone, and we can place our CGS within this limiting zone. The following figure shows the limiting zone as the shaded region for a simply supported beam subject to uniformly distributed load. Thus, for a simply supported beam, if we have a uniformly distributed load, we have a wide depth of the limiting zone at the end. As we are proceeding towards the center of the span, the depth of the limiting zone is getting reduced, and we see that the locus of E min and the locus of E max are the upper boundary and the lower boundary of the limiting zone for placing the CGS. Let's now try to understand this concept by solving a problem. For the post-tension beam with the flange section as shown in the next slide, the span is 18 meters. For uniform loads, the profile of the CGS is parabolic. The live load moment at mid-span, which is represented as MLL, is 648 kilonewton meters. The pre-stress after transfer P0 is 1600 kilonewtons. Assume 15% loss at service. Evaluate the limiting zone of CGS if the allowable stresses at transfer and at service are as follows. For compression, the allowable stress is 80 Newton per millimeter square. For tension, the allowable stress is 1.5 Newton per millimeter square. In this problem, we are having the allowable values same for transfer and service, but in general, these values will be different because the strength of the concrete will be different at transfer and at service. The section is an unsymmetric I section where the top flange width is 500, the bottom flange width is 250 millimeters. The total depth is 1000 millimeters. The depth of both the flanges is 200 millimeters, and the width of the web is 150 millimeters. The CGS is intended to be located at a distance of 150 from the soffit of the beam, and for this particular beam, we want to find out the limiting zone for placing the CGS throughout the span of the beam, and the span length is 18 meters. First, we are calculating the geometric properties. Since the section is unsymmetric, we need to locate the CGS, which is not at the mid depth anymore. The the section is divided into 3 rectangles for the computation of the geometric properties. The centroid of each rectangle is located from the soffit. For the first rectangle, the centroid is 900 millimeters from the soffit. For the second rectangle, the centroid is 500 millimeters from the soffit, and for the third rectangle, it's 100 millimeters from the soffit. We intend to find out y bar, which is the distance of the CGS from the soffit, and once we have determined y bar, we can calculate CT, the distance of the top from the CGC, and CB, the distance from the bottom from the CGC. Now CB is equal to y bar. The area of the section is given as the summation of the areas of the 3 sections. Area of 1, which is A1, is equal to 500 times 200, equal to 100,000 millimeters square. Area of 2, which is A2, is equal to 600 times 150, equal to 90,000 millimeters square. Area of 3, A3, is equal to 250 times 200, is equal to 50,000 millimeters square. Thus, the total area A is equal to A1 plus A2 plus A3, which is equal to 240,000 millimeters square. The distance of CGC from the soffit is given as the summation of the first moment of the individual areas divided by the total area. The moment of the first area is A1 times 900. The moment of the second area is A2 times 500, and the moment of the third area is A3 times 100. All these 3 distances are the distances of the centroids of individual rectangles from the soffit of the beam. Divided by the total area, which we have just calculated, gives us the value of y bar equal to 583.3 millimeters. Thus, the CGS is located at a distance of 583.3 millimeters from the soffit of the beam. CB is equal to y bar equal to 583.3, CT is equal to 1000, which is the total depth, minus 583.3, equal to 416.7 millimeters. Moment of inertia of 1 about axis through CGC can be computed by the parallel axis theorem. I1 is equal to the moment of inertia about the centroid of the rectangle plus the area of the rectangle times the distance square. Thus, I1 is equal to 1 by 12 times 500 times 200 cube plus A1 times 900 minus 583.3 whole to the power 2, and we get a value of I1 equal to 1.036 times 10 to the power 10 millimeter 4. Similarly, we can calculate moment of inertia of area 2. This is equal to the moment of inertia about its centroidal axis, which is 1 by 12 times the breadth, which is 150, times the depth cube, which is 600 to the power 3, plus the area, which is A2, times the distance square. The distance is 583.3 minus 500 whole to the power square, and once we substitute the value of A2, we get I2 is equal to 3.32 times 10 to the power 9 millimeter to the power 4. Moment of inertia of 3 is also available similarly, that I3 is equal to the moment of inertia about its centroid plus the area times the distance square, and once we substitute the values, we get I3 is equal to 1.184 times 10 to the power 10 millimeter to the power 4. The total moment of inertia of the section I is equal to I1 plus I2 plus I3, which is equal to, once we substitute all the 3 values, we get I is equal to 2.552 times 10 to the power 10 millimeter to the power 4. Next, we are calculating the moment due to self-weight. The distributed self-weight is equal to the unit weight of concrete, which is taken as 24 kilonewton per meter cube, times the area, which is 240,000 millimeter square, times a factor which converts the millimeter square to meter square. This gives a self weight of 5.76 kilonewtons per meter. The moment due to the self weight MSW is equal to the weight times the span square divided by 8. The span is 18 meters and the self weight is 5.76, and after substituting the values, MSW is equal to 233.3 kilonewton meters. At this stage, we are having the properties of the section. We know the self weight, and now we are moving on to calculate the limiting zone. The values of Emax and Emin are determined by equating the stresses at the edges of concrete with the allowable values. To recollect, the expression of stress is given below, that the stress at a depth is equal to the uniform compressive stress, which is minus P by A plus minus PEY divided by I, which is the varying component due to the eccentricity of the pre-stressing force, and plus minus My by I, which is the varying component due to the external moment. The summation of these three gives a stress profile which can be compressive throughout the full depth. At midspan, for Emax, consider the load stage at transfer. First, calculate E based on the bottom stress equal to minus 18 Newton per millimeter square, because that is the maximum compressive stress that we can have. Therefore, we are finding out the individual components in the expression of the stress. Minus P0 by A is equal to 1600 times 10 to the power 3 to convert it from kilonewton to newton, divided by the area, which is 240 times 10 to the power 3 millimeter square, gives me a stress of minus 6.67 Newton per millimeter square. This is the uniform component throughout the depth. The next is P0 times E times CB divided by I, which gives us the stress at the bottommost fiber due to the eccentricity of the pre-stressing force, equal to minus 1600 times 10 to the power 3 times E, which is the unknown quantity now, times 583.3 divided by 2.552 times 10 to the power 10, and this gives me an expression of minus 0.0366 E. Thus this component of the stress is in terms of the eccentricity E. Next, we are calculating the component due to the self weight. MSW times CB divided by I is equal to 233.3, which we just calculated, times 10 to the power 6 to convert it to Newton millimeters, times 583.3 divided by the value of I, which gives me a stress of 5.33 Newton per millimeter square. Thus, the total stress at the bottom is equal to minus 6.67 minus 0.0366 times E plus 5.33 equal to minus 18 Newton per millimeter square. Thus, we are equating the stress to the allowable value, from which we are computing the maximum value of E, which is denoted as E max. Solving, E is equal to 18 minus 6.67 plus 5.33 divided by 0.0366 gives me 455.2 millimeters. This value of E is based on satisfying the compressive stress at the bottom. Let us now calculate E based on the tensile stress at the top. For the tensile stress at the top, the uniform component is already known, which is minus 6.67. The component due to the eccentricity of the pre-stressing force equal to P0 times E times CT divided by I, and here CT is equal to 416.7, and we get an expression of this component equal to 0.0261 times E. the value due to the self weight is equal to MSW times CT divided by I equal to minus 233.3 times 10 to the power 6 times 416.7 divided by the value of I gives me a compressive stress of minus 3.81 Newton per millimeter square. And once we substitute this for the total stress at the top, then minus 6.67 plus 0.0261 E minus 3.81 gives me the allowable tensile stress at the top, which is 1.5 Newton per millimeter square. Once we solve E, we get a value of 460.8 millimeters. Now, out of the two values, the lower value, which is 455.2 millimeters, governs, and that is the one which is selected as the maximum eccentricity for the CGS at midspan and which are based on satisfying the stresses at transfer. Next, we are calculating the minimum eccentricity for the load stage at service. We are proceeding with a similar set of calculations, and here we are satisfying the top stress to be minus 18 Newton millimeter square. The effective pre-stress by the area is equal to 85% of the pre-stress at transfer divided by area, and which is equal to 0.85 times minus 6.67 gives a value of minus 5.67 Newton per millimeter square. Thus, this is the uniform component at service after the long-term losses. PE times E times CT by I, which is the value of the stress at the top due to the pre-stress at service, is equal to 0.85 times 1600 times 10 to the power 3 times E times 416.7 divided by the value of I gives me a value of 0.022 times E. The value due to the live load moment is equal to 648 times 10 to the power 6 times 416.7 divided by the value of I is equal to minus 10.58 Newton per millimeter square. Thus, the stress at the top is the uniform component, which is minus 5.67, plus the varying component due to the pre-stressing force, which is in terms of E, which is 0.022 E, minus the value due to the self weight, which is 3.81 Newton per millimeter square, minus the value which is due to the live load, minus 10.5 Newton per millimeter square. Remember that here there is no other superimposed dead load other than the dead load due to self weight. Equating this top stress to minus 18 Newton per millimeter square, the allowable value, we are able to calculate the value of E equal to 93.6 millimeters. To calculate the E based on the bottom stress, which can be tensile, equal to 1.5 Newton per millimeter square, we know the uniform component. We are just deriving the component due to the eccentricity of the pre-stressing force, and here we are using CB for the bottom point, and once we substitute the values, we get PE times E times CB divided by I equal to minus 0.031 times E. The stress due to the live load is equal to 648 times 10 to the power 6 times 583.3 divided by the value of I is equal to 14.81 Newton per millimeter square. Once we have substituted these values at service, the bottom stress, which has the uniform component, the component due to the pre-stressing force, the component due to the self weight, and the component due to the live load, the total stress at the bottom can be 1.5 Newton per millimeter square, which is tensile. Solving, E is equal to 418.4 millimeters. Out of the two values of E, the higher value of 418.4 millimeter governs, because if we still reduce E, then we shall have tension which is larger than the stress at the bottom, and hence we have E minimum is equal to 418.4 millimeters. Thus, we have found out the two extreme values of the CGS at the midspan of the section. Similarly, we can find out the limiting position at the end. For the end, the moment due to self-weight and live load is equal to 0. Going through a similar procedure at transfer with FB, the stress at the bottom equal to minus 18 Newton per millimeter square, we find out an eccentricity which is equal to 309.6 millimeters. And by equating the stress at the top, which is 1.5 Newton per millimeter square, we find out an eccentricity of 314.2 millimeters. Selecting the lower value of the two, we find out E max at the end equal to 309.6 millimeters. Similarly, for service, we are calculating first based on the tensile stress at the bottom, which can be 1.5 Newton per millimeter square. Based on that, E is equal to minus 223 millimeters, and by equating the stress at the top to minus 18 Newton per millimeter square, we find E equal to minus 436 millimeters. Since the values of E are negative, the CGS can lie above CGC. The position of CGS closer to the CGC is selected. Thus, out of the two values, whichever is numerically smaller, we are selecting that value, and E minimum is equal to minus 223 millimeters, and here the CGS can lie above CGC. Similarly, the values of E max and E min can be determined at regular intervals along the span. The limiting zone is available by joining the points by straight lines. In the following sketch, the limiting zone is shown shaded. Thus, for this particular beam, at the center, we have a very small depth of the limiting zone, which is ranging from 418.4 millimeters to 455.2 millimeters, whereas when we come towards the end, we have a wide depth of the limiting zone. Here the CGS can lie above the CGC up to a height of 223 millimeters, and it can lie below the CGC up to a depth of 309.6 millimeters. This blue region is the limiting zone of placing the CGS along the span of the beam. From the sketch of the limiting zone, it is evident that the tendons can be spread out at the ends. This is necessary to anchor the tendons and reduce the stress concentration at the ends. The following photo shows the spreading of the tendons near the end. In this photograph, we see that the tendons are more concentrated towards the midspan, but as we are moving towards the support, the tendons have been spread out. This is helpful. First, it helps us to anchor the tendons. The anchor blocks are spread out at the end, and also the stress concentration has been reduced because the anchor points are spread out. Hence, what we observe that for in a simply supported beam subjected to a uniformly distributed load, we have a limiting zone which is small in depth at the midspan, but it is larger in depth at the support, and this is helpful for placing the tendons and anchoring them at the end. We are learning one concept which is helpful in avoiding stresses going beyond the allowable values, and this concept is called post-tensioning in stages. In the previous expressions of E max and E min, the values of P0 and PE can be for different levels of pre-stressing for post-tension members. At transfer, the member can be partially pre-stressed in the casting yard, from which P0 is calculated. After the member is placed in its permanent location, it can be further pre-stressed before it is put into service. The application of pre-stress in different stages is termed as post-tensioning in stages. The value of PE is calculated from the revised pre-stressing force. The example that we have solved, there both P0 and PE were due to the same pre-stressing force at transfer. But we may apply the pre-stress in stages. That first, in the casting yard, we apply the pre-stress partially, for which P0 is low and we can avoid cracking at the top. Next, after we have moved the member to its permanent location, we can increase the pre-stressing force. By this, we have also reduced the chance of a higher loss in the pre-stressing force. Now, once we re-stress the tendon, the value of PE is calculated from this new value of the pre-stressing force, and we will be able to sustain higher load because we are compensating to a certain extent for the losses, and hence the post-tensioning in stages is a viable option in practice to reduce the effect of losses in pre-stress and the chances of the stresses going beyond the allowable values at transfer, because at transfer we are having a lower pre-stressing force. As we move on to the application of service load, we are increasing the pre-stressing force, and by that time the concrete has attained more strength and its allowable values have gone up, and that is helpful for the pre-stressed member. With reduced P0 at transfer, Emax is increased. Thus, the limiting zone for placing the CGS and the available zone for the shift in C under service loads are also increased. Thus, partial pre-stressing at transfer helps us to increase the limiting zone. In today's lecture, we studied three important concepts of design of members for flexure. First, we studied the choice of sections. As we know that the sections can be varied types depending on the type of application, then the technology available and the money that is available for the construction. We have divided the sections into four broad groups: the rectangular section, the T section, the I section, and the inverted T section. We saw certain variations of these sections. We can have a taper section, we can have a bulbed T section with a bulb at the bottom of the web, we can have a box section whose analysis for the primary moment is similar to an I section, and we can have a U type of section which is similar to an inverted T section. Now, each of these sections has its own merits and demerits. Depending on the type of application these sections are selected, we find that for long span structures we prefer to have the I section or the T section. For conventional small span buildings, we can have rectangular section, and we can use inverted T section only if we have a cast in place flange at the top. Next, we moved on to the determination of the limiting zone. The limiting zone helps us to place the tendons throughout the span of the beam, and we find that for a simply supported beam, the limiting zone is deeper at the ends and has small depth towards the midspan. This helps us to spread out the tendons near the ends for anchorage and reducing the stress concentration. We can also go for post-tensioning in stages so as to reduce the detrimental effect of pre-stress at transfer. With this, we are ending the design of members, and in our next lecture we shall move on to a graphical method. Thank you.